I started out, Nick, giving you the idea of work equals force times distance. And normally on your test, there would be several questions involving work. But because I'm cutting corners with the COVID thing, your test is going to be on the law of conservation, of energy, GG. And then one question where I ask you to figure out the power of something. And I'll even be more specific. It's going to be a multiple choice question, a little one marker. I'm going to ask you to calculate probably the power involved in lifting something. Power is work over time, so it's going to be mgh over time. Or I'll give you the power and ask you to find the time. Or I'll give you the power and ask you to find the m. Or I'll give you the power and ask you to find the h. But it's going to be lifting something. Get one of those by itself. But the written section is going to have some conservation of energy, GG. Just so that you're clear on the concept. When we say energy is conserved, what we're really saying is the total energy can't change. Let me give you an example. At the bottom here, how much potential energy is there in your head? Actually, you can read it. How much kinetic energy is there? What's the total energy? What's the total energy? What's the total energy anywhere? 75, which means at the top, if I have no kinetic energy, it must all be potential. And if you told me the mass, I could figure out the height, because I could go that equals mgh, divided by mg. As I slide down, I lose potential energy. What's that energy turning into? How many joules of kinetic? And by the way, if I knew the mass, I could let that equal a half mv squared and solve for v. How much potential energy here? Okay. This is that skateboard ramp app that I showed you where the total energy remains the same, but potential is turned into kinetic, potential is turned into kinetic if we're ignoring heat. As an equation, we said this. The energy that you start with equals the energy that you finish with. Although if the question talks about heat, then we'll just add heat over here. So if, for example, I had 0 initial and 75, like at the top, and if at the bottom I ended up with 65 and 0, I would say, I guess 10 joules went into heat. Okay. Let's do some physics-y related questions. Suppose the 320 kilogram coaster below, I'm going to make a brand new question. Now it's 425 kilograms. At rest, at the top of the first hill, and it's given a very gentle push. I'm going to change the height of the first hill. Instead of 90 meters, I'll make it 110 meters high. How fast will it be going at location A? We could, in theory, find a velocity by finding an acceleration. The problem is to find the acceleration, I would need to use that slope and that slope and that slope and that slope. This is why we use a scalar approach. You can do it, by the way, with winner minus loser, but you need calculus because you actually have a changing theta, and it's doable, but no one would do it that way. Instead, is there a change in height? Is there a change in speed? Is there a yucky curvy path? We're going to use or any of these 0. When is KE 0? KE is 0 if V equals 0. And what's our fancy phrase in physics for V equals 0? At rest. PE is going to be 0 if we're on the ground, if H is 0. Now, I got to be careful. Potential energy here is actually gravitational potential energy. There are many other ways to store potential energy. This battery right now has some PE in it, not because of its height, but because of electric chemical stored energy. But for the purposes of what we're doing here in physics 12, generally potential energy is stored due to MGH. The exception to that was the bow and arrow question or the slingshot question that we've looked at. And I'm not putting one of those on the test because I haven't. Normally that's one that always goes on the test because they're cool. I haven't had a chance to really help you separate those two and percolate those two. You haven't had enough time. I'm making you drink from the fire hose. In this question, if I let that be initial and that be final, which of these are 0? At rest. So KE initial. So my equation gets modified to all of the potential turns into kinetic. And that's what every roller coaster does. Although in real life, because there is some friction, in real life, we would lose a little bit of kinetic energy to heat. But we grease it down pretty good. Okay. So I end up with oh, I noticed something. What do you notice? Have you gone on a roller coaster before? Yeah, before you went on the roller coaster, did you have to step on a scale? No. Why not? Masses cancel. Now, in real life, if there was heat, the heat would drop down, and technically there's no mass in heat, but as long as we grease it down really good, keep heat to a minimum, an empty coaster, you may have seen, an empty coaster will make it through the track the same way as a full coaster. So in real life, M is negligible, but in our magic physics world, M cancels completely because, nice math. As far as I'm concerned then, I can either give you the height and say find the speed, or give you the speed and say find the height. Here, we're finding speed, times by 2 square root. So it's going to be 2 times 110, well, times 9.8. Put the 9.8 where the G is, Mr. Duke. Times 110. I doubt very much this will work out evenly. Square root. 46.4. This is a good coaster. Oh, heck yeah, that's a good. Probably I've made up unrealistic numbers, although I know there's a couple in the US that crack 100 miles per hour, which is only a little less than that. So they're out there. There's the Top Flight Dragster, which I think is in Cedar Springs or Cedar Rapids, Ohio. There's a big amusement park in Ohio that's got some of the best rides. But hey, yeah, I'd go on this. Is good. Okay? So in this situation, I gave you the height and said find the speed. I could also give you the speed and say find the height. So suppose at location B, the coaster is traveling at 12 meters per second. How high is hill B? Now, that's final. I could move initial to here as long as I was sure this answer was correct, but I'll show you, if I hadn't done part A, how I would handle this. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? Okay. Are any of these 0? I think just initial kinetic. And so I'm going to end up with this. Potential energy initial equals kinetic energy final plus potential energy final. I'm going to end up with mgh initial equals a half mv final squared plus mgh final. Marcus, have you gone on a roller coaster before? Before you got on the roller coaster, did they make you step on a scale? Why not? Oh, that's cool. And I guess it wants me to find that. I guess I'll minus 0.5 v squared over, and then divide by g. Okay. I don't know if I gave you one like this in the homework. I probably did. I should have. Anyways, it looks like the height of that hill is going to be gh initial minus 0.5 v final squared all over g. Okay. G, 9.8. H initial, I think, was 110 minus 0.5 times 12 squared all over 9.8. Look for typos. GH minus 0.5 V squared. I think that's right. that seem right? Well, yeah, 12 meters per second. Remember at the bottom it was going 40 something. 12 meters per second, it's almost lost all of its kinetic energy. How would it lose almost all of its kinetic energy? It's almost gone back to its original height. See, I'm okay with that. 102.7. If I got an answer bigger than 110, that's impossible. That means somehow it's gained energy from nothing. Okay. Now, there are tracks in real life where it's not a closed system. You actually gain some energy at a later point. There's a little booster or whatever. Or I know in California Screaming, because I've been on that one a whole bunch of times, there's a spot where they deliberately have to break you to slow you down. They have to bleed some energy off. And then you keep going. So you hit a spot, and there's a bit of a jerk as the air brakes or something slows you down a little bit. What else could I ask? So right now, I'm saying, give me speed, find height. Give me height, find speed. In other words, in my conservation of energy equation where there's 4 terms, as far as I'm concerned, you can get this VI by itself, or this HI by itself, or this VF by itself, or this HF by itself. Bonus if some of them are 0, but even if they're not, it's doable. Here's some conceptual stuff. Let's look at the skydiver on the right here, the person who's diving from the diving board. How much potential energy are they starting with? Can you see? 15,000? How much kinetic? So this is stuff that I normally do in Physics 11, which I think makes this more intuitive. This is why I'm kicking myself. I should have done it with you. What's their total energy? What's their total energy right here? What's the total energy right here? What's the total energy anywhere? Okay, so as they fall, they lose potential, gaining kinetic. So if right here they have 11,250, how much kinetic energy do they have? 15,000 minus 11,250. They've got 3,750 joules. Halfway down, they've got half the energy as potential. The other half is kinetic. And when they reach the ground, no potential. It's all kinetic. That also means you're traveling your fastest right when you hit the ground, which again is kind of a Captain Obvious. Not 11,250, Mr. Duke, 15,000, right? So it's a Captain Obvious. Well, of course you're traveling your fastest right when you hit the ground. But there's the physics of why. Okay? You can think of it in 2 ways. One way to think about it is gravity is accelerating me, but another way to think about it is in terms of energy. 2 different ways to look at the world. This little slopey hill here, what's our total energy? 50. So we must have started out with 50. Halfway down we have 25. And the beautiful thing is, because energy is a scalar, I can analyze a curvy, yucky path. Okay? How much energy do I have in this picture here? What am I starting with? So it all turns into kinetic. What am I starting with? Still 30, because it doesn't care about the path. What about here? 30. What if I go 1/3 of the way down? 20, and now 10 joules would be kinetic. 10 potential, 20 kinetic. What would my final kinetic energy here be? It would all have turned into kinetic, because no potential. The fact that kinetic energy is a half mv squared. V what? V what? Look at the pattern here. We're going 30 kilometers per hour. We're going twice as fast. How much more energy will I have? 2 squared as much. What is 2 squared? So instead of 10 to the 6th, it'll be 4 times 10 to the 6th. What if, comparing it to 30, I'm going 90 kilometers per hour? How many times faster is that? 3 times faster. So 3 squared is, I'll have 9 times the energy. I'll have 9 times 10 to the 6th. And this also means because I have 9 times the energy, I'll take 9 times further to stop at 90 kilometers per hour than I will at 30 kilometers per hour. And just that alone explains a lot of car accidents. People just assume, well, twice as fast, I'll need twice the distance. 4 times the distance, thank you very much. Okay. Yeah. So twice as fast, 4 times bigger than the original answer.
Never mind now.
3 times as fast, 9 times bigger than the original answer. Okay. And also, because you're all young, dumb drivers, in reverse, if you're in an accident at 90 kilometers per hour versus 30 kilometers per hour, you'll have 9 times the damage. Slow down. It's not worth getting there 5 minutes early. It really isn't. Slow down. Oh, also, again, once you start paying for your own gas, okay? Let's just compare doing the speed limit 60 with speeding at 90. Look how much more energy you're using, 5 times 10 to the 6th more. You're burning gas way faster. It's way more expensive to speed. I have a sailboat, and I've learned if I got to get somewhere fast, I'm willing to, but its cruising speed is 6 knots, which is right around 6 miles per hour. It sips the fuel. But I can get it up to 18 knots. I did it once to see if it could. Okay, I'm using 9 times the gas. Now I'm burning through gas in a hurry. It has to be, because on a sailboat, I'm trying to relax anyways. I'm not going anywhere fast anyhow. It's got to be a pretty darn good reason for me to do wide open throttle as far as I'm concerned. Otherwise, I'm happy to just sip the fuel, save the money. My car has a little economy button, a green light that goes on, and I can tell exactly when it goes off when I'm using way too much kinetic energy, and that squared kicks in and I'm burning way more fuel than I should be. Yeah? Let's do some more roller coasters. Okay? So here's another one. I'll change it. How about we'll make it a 30-meter high ramp, and we'll make this 90 meters long. So 30 meters. And that means it's probably traveling a little faster. I'll have it traveling at 18 meters per second. I hope this will work. I'm doing some quick math in my head. It may end up, because I made up numbers, that it can't get to 18 by the time it gets to the bottom, in which case I'll change it. What's it want me to find? How much energy is lost to? So I would say this. Is there a change in height? Yeah. Is there a change in speed? Yeah. Is there a yucky curvy path? No. But are they talking about heat? This is conservation of energy, with the heat part of it. So it's going to look like this. KE initial plus PE initial equals KE final plus PE final, and whatever is left over went into heat. Starts at rest, yay! Ends up on the ground, yay! Probably on your test, because I think this is a little easy, I wouldn't start it at rest. I might have some kinetic energy, or I wouldn't have you on the ground. I wouldn't have 2 terms cancel out. It's a little easy. How would I get the heat by itself? How would I move the KE final over? Subtract. Every year I have some kid that divides for some reason. I don't know why. So I'm going to end up with this. PE initial minus KE final equals heat. Okay. So the heat is going to be mgh initial minus a half mv final squared. It's going to be m. What did I say m was, Mr. Dewick? 75 times 9.8 times 30 minus 0.5 times 75 times 18. Don't forget the squared. Ooh, I'm getting nervous here. That squared is going to maybe make a bigger difference than I planned. Let's find out. 75 times 9.8 times 30 minus 0.5 times 75 times 18. Please give me a positive answer. Whew. Double check my typing. That looks good. So we're missing 9,900 joules. It must have gone into heat. Okay. Follow-up question. What's the average force of friction? Now, normally my first thought would be did they give me a coefficient of friction in this question? A mu? No. In fact, did they give me a theta? No. And normal force would be mg perpendicular. Now I could technically figure out theta because this is a triangle that has a 30 and a 90, and I could go shift sine and figure it out. But what did I just find in part A? You know what? Heat is the work done by friction. So rather than trying to go mu times the normal force, I would say I think 9,900 equals the force of friction times distance, force times distance. How would I get the force of friction by itself? I'll get friction equals 9,900 divided by d. Which d? So the force times distance equation, the force and the distance have to be in the same direction. If friction is acting in this direction, 90. And holy smokes, by a fluke, this is going to work out evenly. 110. And that's a force, newtons. An old scholarship question, which was meant to be really tough, gave you this setup, gave you this statement, but instead of asking how much energy was lost to heat, they asked you to find mu. So you walked through this to get the 9,900, then you walked through this argument to get the 110 newtons, then you went shift sine of 30 over it to get theta, and then you could say mg perpendicular of cosine, and you could get the mu by itself. It was a nice question. It was once you spotted the way to get there, it was just a lot of writing, but it was kind of cool. I'm not going to give you one anywhere near that tough, but we can certainly handle it. In fact, I'm almost deciding I might put one of those in the homework next year, because one of the things I want to do next year is I need to make the homework tougher. In Physics 11, I do an okay job of making the homework tougher than the tests. I don't do that well enough in Physics 12. To me, the test should be the easiest thing. Anyways. What can I do with something like this? Well, let's supposing I told you that is there a change in height? Is there a change in speed? Is there a curvy path? Conservation of energy. Okay. PEI is not a real province. We all know that. It's an island. Their premier is not a premier. They're a mayor at best, right? Anyways, I think at the top, I'd be slowing down, come to a stop. Okay. By the way, I could replace this picture with a swing set, same physics. This is why conservation of energy is so nice. It's very powerful. Anything where you got a yucky, curvy path. So swing set at the bottom, your potential energy is 0 if we let the bottom be right where you're sitting. We let ground level be there. And that is one of the nice things about conservation of energy. Josh, you can make the height of 0 wherever it's most mathematically convenient. So even though technically if you're on a swing set, you're technically not on the ground, you're about a meter above the ground. Put the ground right where the swing is. You'll be good. So this ends up being pretty simplified. I get a half mv squared equals mgh. Can little kids and grown-ups ski next to each other holding hands? Yeah, why? Okay. And this one's a bit more even better than the roller coaster because with snow, not much friction in real life. Okay. So in fact, in real life, the biggest one, so if you're a big grown-up and you're holding the hand of a little kid, the biggest issue is you have way more air resistance because your body is so much bigger. That's what you have to, in real life, adjust your skis for slightly. But the friction part of it is pretty minimal. Pretty minimal. How do I get the h by itself? Yeah, I get this. H equals V squared. And I wrote VF there. I should have put an initial there. You guys were probably catching that. VI squared, and then over 2G. I can write it that way, or I can put a 0.5 in front of the VI. I don't care which. 4.6 squared divided by 2 times 9.8. For skiing, 4.6 meters per second is not very fast. I doubt we're going to get a big answer here. Yeah, barely a meter high. Okay. Could I have also given you the height and asked how fast they were traveling? Could I, now in the ultimate review, instead of giving you the speed, they gave you the kinetic energy right here. But again, if I'm giving you the kinetic energy and the mass, I'm giving you the speed. Although, actually, that's even easier. If they gave me the kinetic energy is what goes there. I would divide by mg. So I got lots of options. So again, roller coasters. What's the speed of the roller coaster at point B if 8,500 joules of energy? You know what? Let's change this. Let's make it 16 meters per second. Let's make it 180 kilograms. 16 meters per second. Let's make this a bit of a lousier coaster, not quite as efficient, more friction. Let's put 10,500 joules of energy. Okay. Is there a change in height? Is there a change in speed? Is there a curvy path? Conservation of energy. I'll see if I can fit it in the white space right here. So I would have, are any of these going to be 0? Not the initial kinetic energy. So once you get good at this, Marcus, you start canceling out the zeros ahead of time and not even writing them. Plus, I'm not starting on the ground. I'm not at rest. Ooh, but I'm ending up on the ground, so no potential energy final, but some of the energy went into heat. This is going to be a half m v initial squared plus m g h initial equals a half m v final squared plus heat. Do the m's cancel this time? No m in heat, sadly, so I'm going to have to use this 180. I would minus the 10,500 over. I would go 0.5 m vi squared plus m g h minus 10,500. That equals 0.5 m v final squared. This is around where my love for algebra starts today. Now I guess divide by 0.5 m square root, and I could do that all. I might be tempted just to turn this into a number. Well, this isn't too hideous. I guess I can go divide by a half m square root. And I think I got room to show the numbers here. Let's see. VF is going to be big square root 0.5 180 16 squared plus 180 times 9.8 times 18 minus 10,500, all divided by 0.5 times 180. I'll do the inside of the square root first, so bracket 0.5 times 180 times 16 squared plus 180 mgh minus whatever we lost to heat, close off the top, divided by bracket 0.5 times 180, and then that's fast, square root of that, 22.2 meters per second. That square root or that squared makes it a bit trickier to track stuff in your head. If I double the heat, I don't get half the velocity. It's more complicated than that. So the patterns aren't quite as obvious. This is, I think, pretty much identical to the question we just did. We have an initial velocity. We're ending up with a final height of 0. I told you how much heat. Find V. In fact, I think that's exactly what we did. Yep. So I was going to do that one, but the fact that the question I made up here was the same. Is that all right? That's what we're looking at. Were there any others you wanted me to go over from the ultimate review or from the homework?